I want to first thank you all for taking the time to come and join us here at the ARPA-E Summit. Get going in the morning as our first session here. We're going to be talking a little bit about energy storage. I'm going to start by introducing my colleagues on this session. We've got Srini Mirmar, is a colleague from ARPA-E, Alon Gur, and Dane Boysen. And I'm Mark Johnson, and we're going to spend the next hour or so talking a little bit about where ARPA-E's run some programs on energy storage, and also where we think there might be some opportunities going forward. And most importantly, what we want to get going here is we really want to open this up as a dialogue and really engage the audience with us in this, because there's a lot of things you can do with energy storage. We recognize that. You all are out there on the ground, doing a lot of work in terms of just developing the science and the technology behind this. And we want to hear what are some of the good ideas you think ARPA-E should be talking about and looking at going forward. Now, one of the key things about storage is this is actually a fundamental platform technology for across the energy sector. If you look at the entire use of power and energy across the economy, there's two major sectors of the economy that use energy. One's the electric grid, and the other is the transportation vehicles. So energy storage has the opportunity to transform both of those sectors. It's fundamentally game-changing. That's why ARPA-E really focuses in on energy storage and has a number of programs that are targeting this and looking forward for things like new opportunities in space. Now, if you look in the transportation sector, for instance, weight matters, right? You have to haul whatever your storage technology is around with you. That's why things like energy density and really having aggressive new technologies that can push the envelope around energy density and storage matter, as well as cost. They have to be traded off relative to each other. So looking at where you can quantify a new technology can wind up impacting those two techno-economic performance metrics. Then if you look at the power grid, the issue is cost. Cost. Right? Because getting that cost low enough that it can wind up getting put into the normal cost structure of a utility is a key component. And then having it scalable, having it something that can have sufficient capacity, that's power handling capacity on the grid. Now, those two things strongly are affected by what's the sort of the physics and the chemistry and the technology behind how you actually store that energy and having that storage medium. But there's another really important point about this is you open it up to being a systems level approach. So where can the control system provide greater value? How you can actually take advantage of that physics and chemistry, whatever mechanism you're using in storing energy, so you can wind up getting more out of that. How you can sense what's going on in your storage mechanism and control it in a way so that you can wind up getting the most for that energy storage system. So we're going to talk first about where ARPA-E's already done some work in the transportation sector for storage. So what's the goal here? Well, first is to increase the adoption of electric vehicles. Right? So you hear people like Arun talking about how we import $1 billion of oil per day. Right? Much of that goes to the transportation infrastructure. Now, at the same time, you look at things like renewables, putting up wind and solar. We're not going to be able to solve that problem of $1 billion of oil imports per day unless we've got a way of interconnecting the transportation infrastructure and the electric infrastructure. And energy is the key storage. Energy storage is the key component for that. So if you look at that petroleum utilization, transportation is where the majority of it is, not for the electric power consumption. We want to turn that paradigm on its head. Right? You want to go from having transportation that can be petroleum-based to electricity-based, where the primary fuels wind up being something we generate here in the U.S. So taking as an example, this is just looking at a electric vehicle, an early adoption vehicle. This is the Tesla Model S. It's coming out, and doing some estimates on what does it cost for those batteries. Let's say that's estimates, our estimates based on publicly disclosed information, and what's the pack density and what's the cell cost, right? What this makes clear is what we really would like to be able to get stronger and stronger adoption. go from where we are now to wider adoption, is basically doubling the energy density or more and cutting the cost to half or a third. So that's a really hard technical challenge to be able to get to that point, right? So the challenge is current batteries are just expensive and the energy densities are lower than theoretical maximum. How do we push that envelope further? So if you look at where ARPA-E ran a program called the BEAST program, this is Batteries for Energy Efficient Storage and Transportation. Dane Boysen is the program director on that at this point. We looked at a number of chemistries. There's a lot of possible ways you can wind up storing energy for transportation, going back all the way to lead-acid batteries up to things like lithium sulfur and lithium air. Today, we're looking at about 210 watt-hours per kilogram. BEAST program targets said, how do we get up above 400? So we made a number of projects that we were working on, ranging from advanced metal air batteries, zinc air batteries, magnesium ion batteries, even looking at some advanced lithium ion. How you can wind up pushing the envelope as far as where the current state of the art is, where the future is on that. Then lithium sulfur, and then really high electrochemical potential, lithium air. These are the sort of holy grails of energy storage for the future. Making some good progress in those areas. We're really interested in hearing your ideas about where we can go even further around this. So if you look at how you wind up putting this in terms of the objectives, top level objectives is just to have electric energy storage directly cost competitive with traditional vehicle transportation. Right? How you can make that is just a one-for-one trade-off. You go to the dealer, you say, do I want the electric version or the gas version? You don't have some economic trade-off choice you're trying to make. It's just a straightforward selection of that. So how do you get it at a third of the cost? With 2 to 5 times the energy storage density. And range is really important. This pushes you from the range where you're looking at average daily commuter time, distance, to saying, you know, it's Thanksgiving, I want to go take my electric vehicle and drive up to family members up in New York or something like that. So those are the challenges you can wind up having with making that capability further. Now, it's interesting looking at the range of technologies we've also invested in. It's important to point out it's not just saying we're defining only the solution set has to be electrochemical. We're even looking at things like advanced supercapacitors, and even looking at some advanced manufacturing approaches to wind up getting that cost structure down further and further and further to those targets. So moving from transportation, we can look towards things in the power grid. Before I move on here, I also want to see a lot of people writing down notes on this. I believe these slides are all going to be available in the next few days as well. So let you know that that's where this is going, because we want to wind up engaging the rest of the community on this. So looking for energy for power grid. If you look at the world's electric grid, it's basically the largest economic system that there's no warehousing. You're generating power basically at the same time that you're consuming power. Now in that, there's a number of ways you can wind up using storage. You can use it close to the generation side, or can you use it close to the demand side, the load side. But also it can vary over time. You might want to have very short-term changes that you're trying to balance out of the grid, things like frequency regulation, higher reliability for wind up having a better power on the demand side, down to longer-term solutions where you're trying to do things like increase base load capacity at night, so you can wind up moving generation at night and consuming that energy in the day. Now, ARPA-E has one program, the GRIDS program, that's looking at grid-scale energy storage. It's really important to say what the solution that is trying to solve, or what the problem that's trying to solve, is renewable integration. And the trade-off here is not energy storage, one technology versus another technology. The trade-off is between energy storage and all the other things you can do to try and solve that problem on the grid. So one of the things ARPA-E really takes very seriously when we're looking at new projects, we encourage you to give us some feedback on this also, is where's that techno-economic connection, right? How you can wind up quantifying the cost of providing that service. In the case of renewable integration, you're looking at the cost it would take to provide balancing reserves on the grid to increase renewable integration to higher and higher renewable penetration levels. So we actually went out, took some data. This is data from the power grid in the Pacific Northwest, Bonneville Power, where they have very high percentage of renewables already on their grid. They have over 30% of their current generation capacity is actually wind on the grid today. And this is data, you can actually pull this down from their website on an almost hour-by-hour basis. On the left, you're looking at actually how much wind power is actually generated on their grid and how much they wind up expecting. Right? And so they've got very sophisticated computer controls and modeling, all that sort of stuff you need, weather models, to say, here's where we expect the wind to be producing. But they still have a difference between how much they're generating and how much they're using of the wind. So they balance that with what are called balancing reserves out of the hydropower, literally changing how they use the dam system. That's the graph on the right. What you see is spikes in energy or power that can go up and down by almost a gigawatt. That's a nuclear power plant worth of energy in a 15-minute to an hour basis. So ARPA-E used that data and said, how do we wind up creating a program around this? And you look at what the trade-offs are, we wound up coming up with the grids program. This is the $100 a kilowatt hour target. Duration of 15 minutes to an hour. Where's that $100 a kilowatt hour? This is per kilowatt hour of your capital investment. You say, if I'm going to use that storage mechanism for 5,000 times, so charge it and discharge it 5,000 times at 80% round-trip efficiency, that comes out to about 2.5 cents for every time you charge and discharge that, in terms of every kilowatt hour. Right? That's the differential between that. That's the difference between wholesale price and retail price of electricity. Now you're economically competitive with all of the other technologies that you could use for balancing the grid. Things like pumped hydro and compressed air storage can wind up meeting that in some cases now, but if you don't happen to have Columbia River running through your area, you can't deploy that everywhere. So we want to take the new technologies that are at a higher cost structure than that today and drop them by a factor of 2 to 5 to get below that $100 a kilowatt hour ratio or rate, to wind up developing new technologies that make them adoptable on the grid. This is the impact point. So in doing that, we actually did not select we did not go out and say, this is the type of technology that can satisfy that. We said, there's a range of technologies. Ran a solicitation on that, had 12 projects, range from compressed air storage, superconducting magnetic storage, looking at advanced flywheel storage, number of electrochemical approaches, looking at advanced flow batteries, things like that. Just to give you an idea of where these projects went, and I encourage you to think back to where Eric said, what makes an ARPA-E project in the session before this. So you look at general compression. They came in, they had an advanced isothermal storage technology, and they needed a first scale demonstration they had part of this working at a very, very small scale, and they needed the proof of concept proven out. They had some scientific insight to it, but they had yet to actually prove that out. So we wound up supporting that in a very short duration project, showed that wound up working. It wound up building a bridge so that then the private sector stepped in and said, hey, we can take it from here. And it achieves ARPA-E's goal that we wound up building that bridge, and now they're working with the private sector and actually developing a commercial scale demonstration that's even an order of magnitude larger than this. Then you're looking at something like United Technologies, flow battery technology. It was interesting, in flow batteries, the fuel cell community, some of the things they were looking at for things like very, very high current density power modules had not migrated its way over to the flow battery community. So what we did in that case is we wound up working with them, and they went to very high power density modules in terms of flow batteries and actually have world record power densities at this point. Then down at University of Southern California, this is a new technology that's looking at an iron air battery. And again, trying to get low cost. What do you not like about this? Iron is everywhere. It's ubiquitous on the planet, basically, as an industrial material. And air is free. This is potentially the ultimate low-cost battery. And then at City College up in New York, they're looking at advanced alkaline cell batteries. So if you go down to Costco down the street here, and you buy D-cell batteries, they're not rechargeable, but just buy D-cell batteries. Those come out as about $25 a kilowatt hour. That gives you $75 to figure out how to make them rechargeable, right? So what they're looking at is the chemistry of how do you wind up moving that to making a rechargeable chemistry. So we talked a little bit about some of the technologies that are how you wind up actually storing the energy. The question is now, how do you wind up controlling it? So if you look at the current state of the art for battery management systems, there's very limited sensing. If you look at it in terms of control system relative to, let's say, how your control system on an aircraft works. Very limited. A few temperature points you might take, the whole battery system or in some subsystem of it, you might measure the voltage and the current on it. It really doesn't lend itself well to some active control mechanisms on it. We also have very non-generic, we have non-representative models out there. Basically, the models vary from one manufacturer to the next manufacturer to the next manufacturer. How do you wind up making it a much more ubiquitous model system? So it's not just a rule-based control algorithm, but can be widely adopted. Essentially a plug and store technology. How do we accomplish that? Inaccurate estimation of the state of health in these batteries. Right? There's no, as I like to call it, the battery death meter that says from halfway through its state of life, you know exactly where that life cycle is going to end. Having that is definitely a challenge that we need to wind up addressing. And this all winds up leading into lack of understanding of reliability, safety, and lifetime indications. Right? So you wind up essentially over-engineering the system to underutilize the capacity of that storage mechanism. Right? So up to about 100% excess capacity of the storage is actually designed into the batteries that go into electric vehicles today, just because we lack that capability of doing advanced control, sort of sensing, predictive model control technology. This restricts the utilization, again, the lifetime of these batteries. That affects the adoption of electric vehicles. Same time, you look at something like the power grid, we all agree that you can wind up taking batteries and doing things like community energy storage, especially secondary use of batteries that come out of, say, vehicles at end of life. The problem is you wind up having to characterize those battery systems tremendously before anyone's going to actually put them on the grid. Your non-recurring engineering costs are going to wind up killing you in that case. You wind up needing a control system, though, where the system just automatically, again, sets up that sort of plug-and-store environment, where it understands exactly what its performance envelope is so it can then be moved to the grid as secondary use. This all leads up to suboptimal use of technologies. The picture on the left down in the center there is actually a picture of the battery graveyard in Iraq, I believe. This is batteries that probably still have quite a bit of useful life. Just by lack of good control systems, they're being stacked up and shipped off to a landfill. How can we solve that? By actually using the technology we have better with better controls. So at ARPA-E, we've held some workshops on this, brought a bunch of people together. We currently have an RFI that's out. If you look on it on robust control of energy and storage, this was issued about 2 weeks ago. It'll be running for, I think, until about March 9th as a request for information. Looking at how we can get very low-cost, accurate sensors that you can put down inside of the battery. How can you wind up putting new battery architectures or chemistries together so you can wind up most effectively integrating these into advanced control systems, also at cost, right? You've got this cost-performance trade-off you're going to wind up doing. And how we can more develop better some of the science of the battery models and utilize these better in storage systems themselves. So just to remind you again what Eric said at the start, what makes an ARPA-E project? First question is impact. So I would say in any ARPA-E project that comes in storage, what needs to happen is have that techno-economic connection to say, here's a problem that needs to be solved. We can quantify it in terms of the economic cost it will take to solve it with our technology, with a new technology, versus other storage technologies or other ways of solving that problem. But connecting it back and saying, if we're able to invent a new technology in this area, here's where the impact will be. And of course, transformative technology. Come in and say, no one else is looking at this problem the way we're looking at it. Often this is obviously based in science, right? But often it's bringing together science from disparate fields. Right? How do you bring together people that aren't working together already and say, hey, they're learning this over here and we can apply it in a new way? So there's a lot of breakthroughs, for instance, in power electronics that are just migrating into the storage community. That's a huge area that can wind up getting into the controls area. Building a bridge. It's not sufficient to just say we're going to wind up developing a new technology that's going to have impact. Say, why doing this specific project in this way will it move us from our current state of the technology to a state of the technology that's going to wind up mattering going forward. And the last thing, of course, great people, great teams. I want to thank you all, first of all, for being here. I think having this community is grow and grow at every step of the way is really important for the storage community. So with that, I'm going to turn this over to each of our panel members. We're going to wind up opening it up for some questions as well. I think we've got a microphone in the middle, and we'll go from there. Thank you. Yeah, so why don't we start out, I'm going to go, as people are coming up to the audience here, why don't we go down to each of our panelists here and say, for the programs you're interested in or the areas you're interested in, what's the one or two things you kind of wish someone would invent that you haven't seen out there yet? So, Dane?
All right, I'm on the BEAST program, so I think there's actually a lot of white space out there. Love to hear your ideas, but actually have 5 things that I think are areas where I think we need to invest in as a country. The first is materials for electrolytes. High voltage, high conductivity electrolytes would be enabling for higher power lithium-ion batteries, but also in new chemistries. Obviously, we're investing in new chemistries already, so that goes without saying. The second thing is developing electrodes with extremely long cycle life. One of the major barriers to batteries, particularly at the grid level, is cycle life, because at the end of the day, it's the normalized cost per cycle. So this is a critical area. The third thing that I think is white space and critical to us as a nation is manufacturing of batteries and techniques for manufacturing batteries. If you look at all the major advances in batteries in the last 40 years, they all have been right here in this country. And but they're not manufactured here. So one of the great challenges for us, ARPA-E, and for the audience, I would say, is how do we take our innovation and turn it into products here? So that's going to require another set of innovation. We're never going to be able to match other country in terms of labor, so we got to do it smarter. So that's a big one for me. Fourth one, already mentioned, low-cost sensing. This is critical. It's going to allow us to extend the life of batteries. AC impedance on a chip is an example. I think that is long overdue. I think there's a need for the electronics industry to have a stronger collaboration with the battery industry. I think that there's a white space there. And last, hybrid systems. A lot of batteries are very good, high energy, but they're terrible in power. But you can design them for high power, but they're fundamentally manufactured in a different way. How do we put those two things together? We enter new regimes. And if you look at a Ragone plot, if many of you guys are familiar with that, how do we push ourselves into a new regime in a Ragone plot? So those are the 5 things. New electrolytes, long cycle life, manufacturing, low-cost sensing, and hybrid systems. So that would be my hit list.
So we want to get to some Q&A. I'll just mention a couple things about our existing programs that Mark showed, the BEAST program for transportation and grids and for grid scale storage. I think with those programs, those were areas where there's been a lot of interest, and I think our role was to think about, is there an opportunity for really new science and innovation to be disruptive here if we set a target which is kind of way past what most people would think of, right? So Moore's law for portable batteries, 50 to 70 years for a doubling in energy density. We said, can we do it in 5? Mark, in creating the grids program, said $100 a kilowatt hour, and a lot of people's reaction was, well, for just the power electronics, right? But that was the idea, is, get out of the comfort zone. We have an opportunity at ARPA-E to think that way and say, well, this is what we want to make an impact. And now we have to use our imagination to think about, well, are there any good ideas? And in these cases, there have been. We have another program that's related to energy storage that I just want to mention, which is a bit of a different spin. As opposed to well-known problem, let's set a high bar, we tried to think about, are there really new opportunities for storage? And in this case, it's thermal storage. We have a program called HEATS, which focuses on thermal storage. And we started thinking, well, there's so much interest in transportation batteries, and there's so much interest in the electrical storage community. You start looking at thermal storage media, simplest example, right? Look at phase change in water. And if you calculate the energy densities, I don't know if folks have done it, but you're at about 100 watt hours per kilogram for a block of ice. And so we started thinking about, are there new ways to use thermal storage and maybe get the energy density higher, but could we use it? And in one case in that program, we're looking at, can you actually use thermal storage to accommodate some of the accessory loads in vehicles, right? And reduce your burden on your lithium-ion battery in a vehicle, which is going to be much more expensive than thermal storage. And basically, in that case, you're taking fossil fuel, you're converting it to heat, you're converting that to electricity, you're putting it in your battery, and then you're resistively heating your car, right? So it's a little weird. So that's about the existing program. Quickly on Mark's question, I think there are two areas that have been floating around ARPA-E as pretty exciting that I wanted to mention. One is a question of, the BEAST program really pushed energy density very hard. When we think about driving adoption in electric vehicles, we're really curious about, is there a way to maintain that very high energy density and let you fill up as quickly as you would at the pump? And for those who are in the battery community, you'd say, well, that's just the pipe dream. Everyone knows that energy density and power density are always at odds. And so we've been trying to think about, is there a way to get around that constraint? We've also been wondering, we have BEAST, which is looking at very high energy density for transportation. We have grids that's looking at, we don't care about energy, very low cost. Should we be thinking about a program that's somewhere in between? Should we be thinking about, something that looks like a lead acid type energy density battery, but that can last forever, and still might be useful in various applications? So these are some of the interesting new areas, and hopefully we'll also have a chance to talk about the RFI, because that's an obvious one that we're very interested in.
So I think Dane definitely captured the one part of the essence of the RFI that we have on the street, which is supposed to close on March 9th. But just to answer Mark's question, my dream would be to have an energy management system which incorporates novel sensors, robust aging models, and into a control algorithm, which is the entire energy management system is very tunable with very little effort for different chemistries and different devices. Wouldn't that be great to have?
Great. So if anyone wishes to make a comment or suggestion. Great.
Hi there, my name is Aaron Fike. I'm with a technology company called Energy Cache. I had a question about the $100 a kilowatt hour number. I'm wondering if that is actually a proxy for something that more specifically that you're trying to get to. The reason, if you imagined a pumped hydro facility with a reservoir that would allow you to store 36 hours of energy, it would have an incredibly low $100 per kilowatt hour number, but it really means nothing because there's no point storing energy more than 8, maybe 12 hours tops. And so for batteries, that may make sense, but for systems with a power component and then a storage component, like pumped hydro, that doesn't really make sense. And so is it a proxy for a better measure, like a project IRR or something like that really might be more appropriate for making that comparison?
Yeah, so what it's probably more of a proxy for isn't so much pumped hydro. It's actually looking at what are the other ways you can solve the problem of regulating reserves, spinning reserves out there. And the dominant technology is quite literally putting up a natural gas peaking plant, ramping a coal plant. So doing fast ramping is one option that you'd be wind up trading off. These are much less efficient approaches and saying, can we wind up using storage as a way for achieving that goal of reliability on the electric grid? because that's really what it's a proxy looking for, is saying that it comes down to a couple of cents per kilowatt hour per cycle. And what you're trading off is saying, what's the definition of spinning reserve? So the 15 minutes to an hour actually comes straight out of FERC's definition of what is spinning reserves. Right? And so that's what it's a proxy for. Because, as I said earlier, storage is not trade-off of technologies between one technology and another technology of storage. It's one storage technology versus putting up new power lines, having new generation capacity out there, using demand response, all those sort of things. So it's trying to drive down to that point where it's just economically competitive with that in a rate case or something like that.
Hi, my name is Steve Scuderi, and I'm from a company called the Scuderi Group. For the past 10 years, we've been working with a large independent laboratory in San Antonio, Texas, called the Southwest Research Institute, and we've been coming at the energy storage question from a different angle. We've been looking at compressed air energy for automotive use. And we have developed a engine, actually a working prototype, although we haven't gotten into its hybrid form yet. But our projections say that in our hybrid form, we could potentially get as much as 67 miles to the gallon for a compact car without losing any performance on it. And these are based on very credible predictions by a highly specialized group of engineers that have been dedicated to this thing for the past 10 years. Have you guys ever given any thought to, mediums other than electricity for storage in automotive motivation?
So let me just give a quick answer to that, which is, and I think Mark alluded to this, when we think about new programs at ARPA-E, we're generally trying to think about what's the problem that we're trying to solve, and what are a set of metrics that we could set as targets, which, if you hit them, we believe will solve the problem. But we were very careful to try and construct it in a way where we're not really constraining that to specific technology areas. And so, for instance, in the grids program, the idea was, can you get storage with these characteristics at this cost? And it didn't matter whether you were a battery or a different type of storage medium. I think the other thing that we try to do in our discussions is also, when possible, set the targets at a system level, right, so that new systems approaches can come in. It doesn't happen in every program, but I think it's something we try and do, and anything should fit in. Arun likes to say, you give us a banana that can do what we're asking, and that's fine. We may fund it if we believe it will work.
Okay. You have to provide a credible scientific basis for why a banana will solve it.
Absolutely.
But to answer your question specifically, yes. And in fact, the HEATS program funds a number of these sort of storage technologies, or just thermal storage, that are looking at phase change materials, also looking at compression and phase changes in compression, so looking at what are the working fluids that you could wind up using other than air. And in the GRIDS program, in fact, we've supported set up their general compression. They do isothermal compressed air storage. So absolutely we're looking at a range of possible technology solutions. Should make it really clear to say that it's not that that we're saying these are the only solutions that can solve it. Quite frankly, you could take, Eric says, so for instance, in that very first solicitation, we could have taken all of the projects that were supported by ARPA-E, taken those and not supported them, and supported the next group, and we probably would have had an equal excitement about the opportunity that's there, saying we've got a certain range of, frankly, resources that we can wind up committing to it. We wind up going out and doing some very deep due diligence on the ideas. We spend a lot of time in terms of the feedback we wind up providing, things like that, because we know that these are ongoing problems. We want to continue to engage the community on it, because it's going to take a long road to wind up getting there. We hope to keep working with everyone.
Yeah.
So,
and I can also say, the BEAST program is already out, but if I had a proposal like this as an example of the BEAST program, which was focused on batteries, the target metric was 400 watt-hours per kilogram. If you can do that, and at the end of the day, what you're doing is you're taking electricity, using it to mechanically store energy in a gas. It's the same thing as a battery, only we're taking electricity and storing it chemically. So we don't care. We're technology agnostic. show me the numbers. That's at the bottom line, ARPA-E.
Okay.
If it works, we'll look at it.
Yeah.
Terrific.
I'm just going to mention two last things because I think they're important. One is that you need to keep in mind we're not an extremely prescriptive agency in the sense that our program directors are building these programs with a vision for what problem they want to solve, and they will pull out solutions. And so if we constructed the FOA in a way that unfortunately was more limiting than it should have been, and you propose something, but it still solves the problem, it's not like that's going to get ignored because it didn't really meet the exact piece, right? If it solves the problem, we can still pull it through. The other thing is we have open FOAs that we do occasionally, and that's also for this reason, to be able to capture all the innovation beyond. So
Yeah,
I think we're going to try.
just-
So
We've
just
got,
to
move to one
we've
more.
got a number of people in line, actually.
Oh, sorry. Okay.
Thanks.
Hello, Bill Acker from the New York Battery and Energy Storage Technology Consortium. The issue of longevity, of creating sufficient longevity and proving the longevity in a market that's incredibly conservative, is one of the biggest challenges of putting energy storage on the grid. So I'm delighted that you guys are addressing from the sensor program and also from the longer electrolytes and electrodes program that you're starting to look at. These are very, very important programs. And New York Best is developing a commercialization center that, in addition to prototyping and manufacturing, is going to have extensive testing to look at some of these issues. My question is how, with those programs, we look at studying the longer-term performance of these systems. Accelerated aging, testing in batteries is very unproven and unsure. The work that we funded for sensor development has had some promising results so far, but to have sufficient data long-term is exceptionally challenging. So I'd like to get your thoughts on how we address from a modeling and accelerated aging testing, those kinds of things to go with the controls programs that you're talking about.
So you could use that across all battery storage technologies as well. So you look at not just the controls problem, and you've got a second problem out there. If you look at moving something from the laboratory towards the market, we're not building a first experiment being a battery the size of this room. We're building something that's, the size of this class. Right? So how is that representative of what it scales as it goes up? So it's one of the things we actually put into a lot of our technical milestones is not only prove that this works, show the life cycles, show the accelerated aging, and then show what's the next steps. Why does that move? And then we work very detailed. Actually, Srini spent a lot of time working with people like the Department of Defense, other parts of the Department of Energy. We call that InReach. We work with New York Best, as you know, to try and say, okay, if we're successful in this project, how is it a bridge to the next level? We're not expecting to say we're going to wind up doing all the way to the power grid and have it all at high technology readiness levels. But as we're taking those first steps, how are those technical performance milestones and those technical accomplishments at least checking off the first few? Okay, at least it can make it this many cycles at a size like this before we go to that larger size.
I'll just add, we've got this RFI out on sort of advanced sensing models, controls, and one of the big ideas is, wouldn't it be great if we could dramatically extend the lifetime or improve the safety? One of the things that we really need the community's input on is, if we run a program in this area, how do we set targets to, within a 2 to 3 year ARPA-E program, actually validate that we've done something meaningful? And I think you asked us the question, and I'm going to do this really annoying thing where I turn it back. We think it's important. We think there's a way for us to support it. We need some help thinking about how to do that in a way that folks here feel like, yeah, that's the right way to do it and it's meaningful. So we'd love your input on that.
Right. Well, our members will gladly do that, and I do think that understanding the various life cycles that the things going on become incredibly important in this. So there's a lot of good work to be done. Thank you.
Thank you.
Narasi Sridhar from DNV. Hi, Elon. My question is more of a philosophical question. When we talk about electrical storage, energy storage, are we defining the E part of it too narrowly? In other words, what we want to get out so far in all the technologies that we discussed is electricity out. But we also need a lot of materials. And if you look at the whole material complex today that are required for many technologies, they come from petrochemicals. So is there an opportunity where we think of storage of energy, not in terms of extracting energy out, but getting materials out to do other things, and decoupling petro from petrochemical? And I think if you look at how you want to decouple petro from petrochemical, currently there is only one route, which is biochemical processes. But there could be a lot of technologies that are, some of them are in different stages of evolution, that couple the renewable energies with chemicals. And I wonder if ARPA-E should defocus the letter E a little bit more.
Well,
any comment?
Just two things on that. One is, in the thermal energy program, one of the things that actually came up as we were developing that program was the realization that one way to store thermal energy is actually to store it in chemical bonds and convert it to a fuel. And so part of that program is actually what we're referring to as thermofuels, trying to take thermal energy from the sun and producing fuels with it. But I'd say in the specific question, I'm not sure if the petrochemical question was relevant to this audience, but I'll just say, in looking at the size of the impact, if you look at technologies to create fuels and the size of that versus the amount of petroleum that goes into chemicals, it's actually a small drop in the bucket. And so we're not sure it's a big enough impact for ARPA-E to be looking at for the energy impact.
Having said that, what you're talking about is embedded energy essentially here. And so how does that wind up affecting across the energy infrastructure? Things like a tremendous amount of energy just goes into crushing and grinding rocks in this country, right, as an industrial process. How can we rethink that, right? And that's certainly an area that's really, really important to look at those sort of issues. And that's important because it's in the industrial supply chain. And the techno-economic metrics are really important there, because the question is, who's going to pay half a cent more for some industrial product? So you not only have to develop it more energy efficient, you have to make it better. Right? You have to provide a better service as a result of that. So it's a huge technical challenge. I would agree with you completely. That's an area that we're looking at. We're actually taking very seriously. The area of process intensification. I know Dane spends a lot of time looking at this as well, saying, instead of having 2 or 3 large-scale factories providing something, that slows down actually the rate of innovation. Chemical engineers like to make things bigger and bigger and bigger. You get economies of scale to the point where you have an entire supply chain dependent on 1 or 2 factories. You're not going to change the process in that. That slows down the adoption of innovations. So if you wind up intensifying processes and essentially having small, kind of modular industrial processes, now they can start competing with each other. Now you're going to develop new catalysts and reactors, all those sort of things that'll come out of it. Chemical reactions, things like that. So it's a white space that we're definitely interested in.
So we'll take our first Twitter question.
Thank you. Is ARPA-E interested in behind the meters applications that impact grid availability, i.e. level 3 fast charging?
The answer is yes. Not only that, you look at one of the challenges, and this is relative to storage, is if we start having a massive electrification of vehicle infrastructure, suddenly you're putting a big load out in the periphery of the grid. People start putting level 3 charging in their houses, suddenly you've got a lot of transformers that are 40 years old, that are sitting on telephone poles, that are incredibly stressed. How do we wind up using storage to get beyond that point? I like to think about it as I want the kind of the storage refrigerator that you can put on your credit card. You can go into your local, name it, store, Home Depot, Lowe's, Costco, and for say $1,000 you can buy something the size of your refrigerator that can satisfy the house loads for 2 hours for 4 hours at, let's say, 2 kilowatts or 3 kilowatts, something like that. That'd be game changing. Right? Because if suddenly everybody had one of these items in their house, first of all, if you had some way to monetize between high power times a day, peak, and night, you could wind up actually making money on that in 2 to 3 years. And if you suddenly had that resource in everybody's house at that cost structure, that, I should say, putting it on your credit card, that's the hard technical part of that for anyone that does the calculation. You're talking incredibly aggressive cost targets to be able to do that. That is, again, just for the cost of the metal in the batteries or metal in the power electronics, or you want the battery in that. So things like that are definitely areas we're interested in.
Hi, I'm Heather Sanders. I'm with the California Independent System Operator. And I really, for this community, just want to emphasize the time needed to get this capability there. At the ISO, as recently as last week, we saw at 1 o'clock in the morning 1,000 megawatt up ramp in wind. And so we're struggling to down dispatch all the other resources on the system. So we need cycling up and down a lot, very frequent cycling. We need speed, and we need a lot of flexible capacity on the system, and we need it now. Because what's happening is investment decisions are being made now in what we know we can rely on, and that is, you know, the combined cycle plants we have on the system, because their revenue adequacy is going down with the displacement by the renewable generators. So we are publishing a paper this week about needs for flexible capacity on the system, so I'd encourage you to look at that. We define what we mean by regulation, load following, how much and how quickly. So I just really want to reemphasize that coming in as a system operator. We really like the promise of storage on the system. The problem is cost. Because if you're looking at the utilities investing in these technologies for a 30-year time frame and the cycling that they're going to need, that's where we are. I like the technology, but I wanted to offer that and emphasize that here. Thank you.
Thank you.
Thanks, Heather. Couldn't agree with you more.
I'll just quickly mention one thing that relates to Heather's comment. We have another program that's not represented here called GENIE, which is Green Energy Network Integration, which is all about making the grid more efficient. That's the panel next door, right? All about making the grid more efficient by getting more control over how we route power on the grid and how we dispatch power on the grid. And the idea is, you know, right now the only actuator we have on the grid is the generators, right? And so storage is one piece of that, right? Storage adds a new, right, degree of freedom, adds a new dimension to actuation on the grid. But one of the big problems that this community needs to think about is how are we actually going to decide how to dispatch that power, right? So the example Mark mentioned, if everyone did have a storage system in their house, we really need to get folks like Heather, the system integrators, the grid folks, to think about, okay, how do we operate the storage in a way, and it relates to controls, in a way that's not going to damage the storage and that's going to give the max value to the grid. I think an important component of the problem.
Yeah, so we have about 10 or 15 minutes left here, so let's get on to our next question.
Hello, I'm Dan Vogler with INX Energy Storage Systems in Austin, Texas. First a comment, then a question. Mark mentioned the RFI coming out, or has recently come out, about the control system. It seems like that's focused strictly on the DC side, on battery management of overvoltage, undervoltage, overcurrent, temperature range, cell balancing, or the issues of battery management. This is important because battery management is somewhat crude today, and even the current methodology of the shunt method for cell balancing is 100% inefficient in the way that it works. I'm sorry, I missed your name, the gentleman next to Mark. In your dreamscape, you talked about the power control systems management analytics, which I presume go to the AC side of the storage problem, aside from the DC problem on the batteries. My question is there any RFI or approach today for creating standards around the whole storage architecture? And if not, I would propose to ARPA-E and the DOE that you convene a workshop with industry to create a standard architecture for storage that places the sensors at the load, the grid, the supply, the battery, the control systems within that, and is an agnostic approach, neutral to the form of the battery chemistry, whether it's lithium or lead, compressed air, flow batteries, pumped hydro. All of these are valid methods. The problem today is about a dozen real storage projects that exist in this country have all been engineered over and over again from the ground up as singular projects. We don't have a standard storage architecture for the industry. Is this feasible?
So the RFI is actually not on the AC side, it's the whole system.
It's the energy.
Right, so it's the energy storage system. So if there's understanding how changes inside of, let's say it's a battery or as your mechanism,
could be hybrid, could be multiple devices.
Could be multiple devices, how that can be, how that impacts the entire framework of how that system operates. So it's not just saying it's AC side and controls of things. It's actually AC, DC, you name it. And I encourage you actually to weigh in terms of the RFI.
Think about it more from the module perspective. You know, for just in terms of you could have a single device in there. You could have multiple devices in there for different. It could be a battery in a battery, or a battery in a cap, or a battery or other form. Different devices of energy storage, and how could you really maximize the performance of that energy storage module by implementing some of the sensing and control and sense modeling and control, where you can push these modules to kind of greater utilization, greater lifetime, as well as do it in a safe and reliable way.
I mean, just to be clear, I mean, the RFI on sensing and modeling focuses on a lot of issues that are more specific to batteries, to electrochemical batteries. There's no doubt about that.
It is the mainstay.
There are well-known problems. It's kind of the mainstay. But if you read the RFI, when it talks about the system, we really do want to get ideas of, are there things that ARPA-E should be doing, and if we do a potential program in this area, maybe it gets constructed in that way that capture a whole system approach. So we'd love to hear from you.
As an integrated module perspective, absolutely.
So the current RFI, although specific on DC management of electrochemical batteries, implies a system approach.
We'd love to hear your thoughts on that.
Thank you very much.
Thank you.
Hello, this is Emir Musa from Lightsail Energy in San Francisco Bay Area. We are a startup company. We're trying to develop energy storage system out of compressed air with isothermal process. I have a comment and a question. Comment is whether or not that 15 to 1 hour energy storage is a main focus, because if we can increase that to several hours, that would be a game changer for the energy storage and integration of wind and solar into the grid. Now, my question is whether ARPA-E would consider an energy storage system that is not only an energy storage system, but also can benefit from waste heat, low-grade waste heat, and can also benefit from being a heat engine.
So the answer to your question is yes. If you look at the grids program specifically, it's not in any way saying it's every aspect of energy storage. The specific problem we're trying to solve in that is the one Heather just alluded to. She had a 1 gigawatt wind ramp. That's a 15-minute to 1 hour event last week. That's the equivalent of suddenly having a nuclear power plant show up or disappear on your system. That's a huge challenge for grid operators. So in the grids program, they're specifically looking at that. Saw earlier we put up, there's a range of number of potential uses. And we're not in any way saying that we've covered every one of them yet. And we're interested in hearing from the community of where that can be, where there's other approaches. From grid level, longer duration, frequency regulation, different time horizons, down to the very perimeter of the grid.
We have a session after this on thermal systems, which might be a good area for discussion around the waste heat conversion question.
Thank you.
Looks like we've got just about 5 minutes left.
Good morning. Dennis Mahoney from RCT Systems. Last year you had a joint workshop with DoD on hybrid energy storage modules, and Srini was alluding to some of that there. Can you tell us a little bit about where that stands and what comes next?
So, absolutely. So this effort, this RFI is very much, thank you, Dennis, it's very much continuing our collaboration with the Department of Defense. So if we were to launch an effort in this space, the idea would be that the Department of Defense would be an ultimate customer for these technologies, where we could actually have these integrated modules where the DoD, different service applications which they have identified, would invest and scale them up, which are system specific for their applications. So this is a metamorphosis, or this is how it has morphed, Dennis. And we continue to work that. We continue to work that with ASD-RNE. In fact, the RFI is also on the ASD-RNE and ONR websites as well. So it continues to be a collaborative effort.
Hi, Cyrus Scuderi from CGI Technology. Can I ask a question about thermal heat storage? Or is it the next session?
You're welcome to ask any question you want, but yes.
we will be talking about it more at the next session.
We will be talking about it in the next session.
Okay, so
let's save it for there.
In the next session.
Perfect.
That would
We're going to take one last question.
Yep.
I'm so sorry because we have two, but well, if we make them quick, we'll take the second. Let's see how quick we go. Oh no, we're not going to do the thermal storage one. We're going to save that for next.
I'm a research scientist working for Thomas Jefferson National Lab. My research is on graphene-based supercapacitor. I wonder what's the policy and the vision of ARPA-E and supercapacitors, which is an indispensable part of power storage device. Thank you.
So it's interesting. If you look at capacitors and investment, ARPA-E has actually done a number of products in that. Some in the BEAST program. The others in the power electronics area. So you're looking at the convergence between these technologies. If you look at things like advanced semiconductor switches, which are silicon carbide or gallium nitride based, these new technologies, all they do is they wind up their switch to turn things on and off. If you want to change voltage level, you need capacitors and inductors, right? So it's an essential part of energy management systems, having advanced technologies in that area. So we're of course interested in hearing new technology ideas, how you can again get cost down and energy density higher.
All right, one last quick question.
Okay, thanks. Hi, I'm Katie Hoffner with Pareto Battery, and I believe we're working on some of these wish lists from the entire team up there. But we have a management team that still fits on one slide. It's how do we manage resources and time being the biggest resource? So what's your very best advice on going after this non-dilutive funding from our government?
So you actually, it's good that you gave us the prompt. I just want to say it's important for everyone to hear. Right now we have a draft. We have several drafts on the street. We have a draft of an open FOA. And so we need to be clear that we're giving reactions to things here. Anything that gets proposed to that FOA is going to go through a standard review process which looks at what that FOA says. So if you want to apply to that FOA, look at the FOA, try and compete based on the FOA. What we're saying here is not going to have any impact on how those proposals get reviewed, etc. So that's just an overall disclaimer. I think the slide, what Mark's probably going to say is the slide that Eric Toon showed this morning on what's an ARPA-E project. Big impact in our mission area, transformational technologies, bridging between different disciplinaries, science and engineering, and then really great teams, which are teams that we think will succeed, and also that bring in all the skill sets that are needed to address the problem. That's how you win.
So we've actually, as far as the size of the organization or the team, we have supported as ARPA-E everything from literally one or two inventors that don't have a company yet, that as a result of doing the ARPA-E project, they wind up either having a spin-off from a university or standing up a new organization, up to large companies. And every one of them has a slightly different set of challenges they wind up facing. We want to really work with the community out there. So one thing I'd really suggest you do is there's a number of sessions this afternoon that are really targeted is how do you stand up an organization, essentially? How you can build that community around you so it's not just trying to invent a better mousetrap in isolation, but it's really building that community for your organization that's going to translate that technology breakthrough into ultimately getting the technology out to the market and to commercial success. So, thank you.
Thanks to everyone for their input.
Thank you very much.
We'll be around for the next 3 days, so come find us.